Welcome back to What Did the Code Say? The explainer where we decode the raw, unfiltered logic that keeps your programs breathing. I'm your host, Dragon Megalodon. Today, we're digging into the fundamental math that literally controls every boundary, loop, and conditional statement in your tech stack. It's the syntax of survival. But hey, before we dive into the code, you need to subscribe to the channel and hit the bell. Seriously, do it right now to prevent your next project from completely exploding in your face. All right, let's get into it.
Here's our system diagnostic for today's explainer. First, basic syntax. Second, absolute values. Third, logic gates. And finally, the boss fight. Let's boot this up.
Section 1. Basic syntax. So, think of interval notation as the raw syntax you use to establish the exact boundaries of where your variables are allowed to live. If you don't define these boundaries perfectly, boom, you're looking at memory leaks, out-of-bounds errors, and complete system crashes. Now, notice how we actually lock those boundaries in. If your variable exists strictly between 1 and 3, but doesn't actually include the numbers 1 and 3, you visualize that as an empty circle on a number line. In interval notation, you use soft brackets, regular parentheses. But contrast that against a variable living between -4 and 2, where it's totally allowed to touch those exact boundaries. On a number line, that's a closed, filled-in circle. In syntax, you lock it in with hard brackets, the square ones. Oh, and remember, the smallest value always goes on the left, separated by a comma. Nailing this is step 1 for a stable build.
Now, here's a hard, non-negotiable rule of the system, the infinity rule. Infinity always gets a soft bracket. Why? Well, because infinity isn't an actual number you can physically reach. You literally can't include it. You can only go as far up to it as your system allows. So whether your variable is scaling to positive infinity or dropping to negative infinity, you have to cap it with a soft bracket. If you try to trap infinity in a hard bracket, your syntax is instantly invalid. Your compiler throws an exception and your runtime fails. Period. Always use a soft bracket for infinity.
Moving right along to Section 2, absolute values.
All right, we need to strictly define absolute value as distance to ground you before we jump into the heavy equations. Listen to me on this one, guys, because it's absolutely crucial. It is not just some magic command that turns negative numbers positive. Beginners make that mistake constantly, and it completely corrupts their logic flow. Absolute value is the exact physical distance of a value from 0 on the number line. Keep that actual definition locked in your active memory because it fundamentally changes how we handle the variables trapped inside those vertical bars.
Look at how absolute values actually dictate your code's path. If the absolute value of x is less than 5, you've got a trapped safe zone, because absolute value means distance. The distance from 0 is less than 5. That means your variable is physically trapped between -5 and +5. It lives comfortably right there near 0. But what if the absolute value of x is greater than or equal to 5? Well, then you get split outer paths. The logic forces the variable far away from 0, splitting the number line into two completely separate regions. So x is less than or equal to -5, or x is greater than or equal to 5. You're either pushed far to the left or far to the right. There's absolutely no middle ground here.
Which brings us to Section 3, logic gates.
Okay, fatal bug alert. Listen to me carefully here, because this is exactly where most developers totally destroy their own code. Multiplying or dividing by a negative number acts as a hard trigger that reverses the direction of the inequality sign entirely. Say you're evaluating an expression and you hit a state where -2x is less than -7. To isolate x, you naturally divide both sides by -2. But the exact second you divide by that negative, that less than sign flips to a greater than sign. So your result is x is greater than 7/2. If you execute that division without flipping the sign, your entire logic structure collapses, and your program will validate the exact opposite inputs it was originally designed to accept. Not good.
So the really crucial point is how these rules apply to compound inequalities. We actually process these mathematically just like AND gates versus OR gates in programming. AND statements look for overlapping truths on a number line. You're searching for the exact intersection where condition A and condition B are both colored in and true at the exact same time. If they don't overlap, the set is completely empty. OR statements, on the other hand, look for a union of truths. They are way more forgiving. They accept values from either path. If condition A is true or condition B is true or both are true, the system accepts it. The bounds just merge together like one big happy family.
Finally,
Section 4. The boss fight.
All right, this is where the training wheels fall off, and we stop dealing with simple linear variables. First things first, you need to recognize the traps. Trap number 1, do not just square root inequalities. If you see x squared is less than 4, assuming x is simply less than 2 is a massive trap. Why? Well, think about it. An input like -10 fits less than 2, right? But if you square -10, it outputs 100. And 100 is definitely not less than 4. You just broke the code. Trap number 2, do not clear rational denominators by multiplying them to the other side. You don't know if that denominator holds a positive or a negative variable, which means you have absolutely no idea if you're supposed to trigger that fatal bug we just talked about and flip the inequality sign. Just don't do it.
Instead of falling for those rookie traps, you're going to follow these exact survival steps to keep your logic rock solid. Step 1. Move everything to one side so you have a 0 on the other side. You always want to compare to 0. Step 2. Find your numerator zeros by factoring the equation. Step 3. Find your denominator undefined points. These are the lethal inputs that divide by 0 and instantly crash your system. Step 4. Use test values. Let's say you have x squared plus 6x plus 9 all divided by x minus 1 is less than or equal to 0. You must follow this sequence to map out the valid domains. The numerator equals 0 at -3. The denominator becomes undefined at 1. These two locations are your critical boundary points. By mapping these critical points on a number line, you create distinct intervals. Look at this matrix here. You take test values from between those boundaries, say -4, 0, and 2, and you plug them back into the factored polynomial to create a sign chart. When we plug in -4, the result is negative. When we plug in 0, the result is negative. When we plug in 2, the result is positive. Now, because our original equation wanted to know where the expression was less than or equal to 0, we are actively looking for the negative results. This chart reveals exactly where the equation is positive or negative without any guessing. It mathematically proves that our valid domain is everything from -infinity up to 1.
Defining your exact boundaries and dodging those lethal syntax traps is what separates a stable build from a catastrophic system crash. Mastering these intervals is the only way to keep your code breathing. If you want to understand what the code says before it explodes, hit subscribe.
Don't forget to like. This tells YouTube that technical content is still alive. And hey, take a second right now to share this explainer with a beginner coder who desperately needs some help debugging their math logic.
We've set the limits, charted the intervals, and survived the logic traps. And you, what did the code say in your project today? Drop it in the comments below, and I'll catch you in the next compile.